Hi, everyone. For our next session, we have Amey Kusurkar from GoCardless, a global bank payment company, talking about scaling payment processing beyond $100 billion dollars with YugabyteDB. Amey, over to you.
Thanks, Adam. Hello, everyone. My name's Ameya. I'm from GoCardless, and today I'll be talking about scaling payment processing beyond 100 billion with YugabyteDB. So before we start, just a little bit about myself. My name's Ameya. I'm a senior software engineer at GoCardless. I've been at GoCardless for over 6 years now. So I've seen GoCardless scale processing through different phases of its growth. And over the past year, we've been migrating our payment processing platform from Postgres to YugabyteDB, which is what I'll be talking about today. So before we start, these are the things that I'll be talking about. So I'll start with talking about GoCardless itself, and then I'll talk about how we've been scaling with Postgres up till now. After that, I will talk about how we move towards exploring distributed SQL, and then how we migrated our first workload from Postgres to YugabyteDB, and then what's next, what lies ahead for us. So starting with GoCardless itself. So GoCardless is a global bank payment company. We process more than 130 billion dollars worth of payments annually for nearly 100,000 businesses in 30 plus countries. So jumping right in, this is what a common or typical payment flow looks when it goes through GoCardless. So GoCardless collects payments on behalf of the merchant's customers. So imagine you have a merchant here who's a gym and they'd like to collect monthly gym membership fees from their customers. So we collect the payments on behalf of the customers, we aggregate the funds, and then we settle them with the merchant through a single payout. So we call this the managed fund settlement flow. And this gives the merchant a bunch of benefits, such as providing services like reconciliation, or even the ability to issue refunds back to the payer if they choose to do so. However, today I'm just going to be focusing on the settlement part of the flow. In particular, the daily batch pipeline that runs to process the settlement flow. So this pipeline is fairly database intensive, and this is the focus of the talk. So let's zoom right into that. So this is what the pipeline looks like. It runs a series of steps to determine how much to pay out to the merchant each day. This includes figuring out whether payments have been successful, all the way down to calculating the actual payout amounts to send to the merchant, and then finally executing the payouts by sending instructions to the banking network, where the bank will then execute the fund movements. So this pipeline is quite write heavy. Each step transforms data for further steps in the pipeline. All of this is currently powered by a single Postgres database. And as you can imagine, as the number of payments that we need to settle increases, the writes scale linearly with that. And another constraint on this pipeline is that it needs to complete before the bank settlement cutoff. So banks have settlement cutoffs for daily execution beyond which they don't process payments. What that means for us is that we have a fixed time window to process that day's settlements. And all of this translates to the fact that our settlement pipeline throughput, especially the writes, needs to scale with the payment volumes. So for example, for a given day, if we have twice as many payments to settle, we need twice the throughput so that we can still process everything within the same time window. So let's talk about how we've been scaling with Postgres so far. I'll first talk through roughly what our architecture looks like. We run a large Rails monolith with many components inside. Many of these components are closely related. So for example, you can imagine how the payments API and the payout calculator are both closely related because they both deal with payments. But we also have other components in this application that run non-payment related workflows. All of these components within the application run against a single large Postgres instance. This is a fairly standard high availability cluster. It is self-managed by our infrastructure team, and it has a fairly standard architecture. It has a single primary that serves the read and write traffic, and also replicas to handle any failovers in the event of a failure. So how have we been scaling against Postgres? You can think of this as our optimization loop. On one side, you have things like vertically scaling the Postgres cluster that we have, or extracting non-payment workflows from the database. All of this increases database capacity for the pipeline to increase its throughput. On the other side of the cycle, we also have been optimizing the Postgres workloads to run more efficiently against Postgres itself. What this does is improve database utilization, and you can imagine how we cycle back and forth between these two things to continue scaling the throughput of the pipeline. So one thing that is worth noting is that a lot of the optimizations that we've done so far have been tailored specifically for our Postgres setup. And a good example of this is batch transactions, which is fairly straightforward, just combining transactions together so that they run as large batch transactions rather than individual transactions. So take for example, this transaction workload. It's a fairly standard transaction. We're updating payments, and alongside that, we are updating some other tables as well, because we want the components to be consistent. The important or the interesting part here is the highlighted bit, which is the fact that we are only targeting one payment in this transaction. This means that there are a lot of round trips to the database. If you want to update millions of payments, you have millions of transactions. Lots of round trips adds a lot of latency to the pipeline and affects the throughput. One simple thing that we've been doing, which is fairly effective, is to just change the transactions to be batched. So in this case, instead of targeting one payment, we are targeting multiple payments. In reality, what this means is that each of the statement just updates or inserts multiple rows at a time. This performs really well on Postgres, specifically because it's a single node database. When you give it one large query to work on, all the data that needs to be modified is on a single node. And we've been able to scale this to batches of hundreds of thousands of rows per transaction, and getting more than 4x throughput just through these kind of optimizations. So let's fast forward to 2023. Overall, several years, we've done multiple rounds of this optimization cycle to help us grow several orders of magnitude in terms of throughput. So how are we doing with Postgres today? So unfortunately, we are now approaching the limits of Postgres. We are now running a 64-core instance. This is fairly large, and we are quickly reaching the largest virtual machine instance that our cloud provider can offer. This means that we can no longer vertically scale. We could continue like this for a bit longer, but we would quickly run out of larger instances to upgrade to. We've also done lots of improvements to database utilization through lots of rounds of optimizations, and now we've reached diminishing returns. So what we really need is to horizontally scale our database capacity, specifically because it's a write-heavy pipeline. And that's where we look towards distributed SQL for scaling for our next phase of growth beyond $100 billion worth of payments. So as we started looking out for the right solution, we had a couple of requirements from the beginning. One of them is strong Postgres compatibility. As you saw earlier, we have a large monolithic application which is worked on by several teams, and to keep developers productive and to avoid a potentially large rewrite of all of that code, we wanted a solution that ideally works out of the box with our Postgres workloads. We're also a regulated company, which means that it's important for us to maintain ownership of our customer data, and we want to keep a low management overhead. As you saw earlier, our current Postgres cluster is self-managed by our infrastructure team. And if the infrastructure team spends more time on DB management, it takes away their capacity to do other things that are important to them. This is also one of the main reasons why we rejected a manual sharding approach, because this would just increase the complexity of the database cluster that we'd have to manage. So alongside YugabyteDB, we also looked at some other distributed SQL solutions, but many of them fell short in the first two requirements. Firstly, on strong Postgres compatibility, there was partial support for Postgres features, and also different SQL dialects that didn't quite work well with Postgres queries that we had. And also, there was no solution out of the box that would help us maintain data ownership. The only way we would be able to do that is if we self-manage the cluster itself. So this is where YugabyteDB was a really good fit for us. In terms of strong Postgres compatibility, workloads ran seamlessly. When we did a proof of concept, we didn't have to modify them to work correctly on Yugabyte. We're also able to maintain our data ownership. YugabyteDB has a deployment model called Bring Your Own Cloud, where they can remotely manage your database cluster that is being hosted on your infra, which means that we still retain control of our data. And in terms of low management overhead, YugabyteDB is a cloud-native solution, so we have out-of-the-box solutions for sharding, fault tolerance, recovery, and monitoring. A lot of the things that today we'd have to do manually. So with YugabyteDB selected as our distributed SQL solution of choice, the next step was to migrate our first workload to YugabyteDB. So going back to our pipeline, the first thing we had to do was to pick a good candidate component to migrate. For this, we picked the calculate payouts component. And this was mostly because this was fairly well isolated from the other components already, which means that we would be able to easily iterate on it as we move to distributed SQL. So what we did is that we duplicated that step, subscribing to the same production data that the main pipeline does, but instead pointed it towards a YugabyteDB database to power all the queries. We also added an extra step in this separate flow to just compare the results across the two steps to ensure that YugabyteDB was doing the exact same thing that our main pipeline was doing. But the important thing is that at the end of this, the results were discarded. They're never executed, which means that the main pipeline is never affected. We ended up calling this our shadow pipeline. The important thing here is that this gave the team a safe space to iterate and learn about distributed SQL while using production grade data, and at the same time never affecting our main payouts, so that it wouldn't matter if we got things wrong. There was a safe space to iterate on. So our first goal was to match throughput with distributed SQL compared to what we had with Postgres today. Our aim was to try and do this with similar amount of resources, so same number of database cores, for example. And once we were happy with this, the next goal was to replace the Postgres workload. So the pipeline would now go through the Yugabyte step instead of the Postgres step, which would allow us to migrate to YugabyteDB. So with all of this in place, our shadow pipeline running Yugabyte queries, shadowing the main pipeline, how did we do in terms of our first goal, which was to match distributed SQL, the Postgres throughput? So unfortunately, right out of the box, the YugabyteDB workloads were 10x slower when using the Postgres schema. So this made us step back and think about what exactly is different about YugabyteDB compared to Postgres. And there are a couple of things. So if we just compare the two architectures at a high level, one thing to note is that YugabyteDB reuses the same query layer that Postgres does. What this means is that functionally, queries work the same. So we didn't have to modify the queries itself to ensure that they worked correctly. But beyond that, that's where some of the major differences come. So one thing is that Yugabyte, unlike Postgres, is a multi-node database, which means that the data is distributed across nodes, and multiple different nodes are involved when executing queries, aggregating queries, so on and so forth. And another big difference was that the storage layer technology itself was different. So YugabyteDB uses something called DocDB, which is different from the Postgres storage layer. And the implications of these are things like it uses different data structures to store its data. all of this which will have impact on the performance of the queries itself, which we'll see shortly. So basically, all of this just told us that even though workloads are functionally compatible from Postgres compared to Yugabyte, you can't just naively migrate them over because under the hood, it's still a different technology. So as we progressed, we worked closely with the Yugabyte team to understand how Yugabyte differs from Postgres and identify optimizations to improve the throughput. So today, I'm just going to share the top 3 optimizations that we think had the most impact in terms of improving throughput. So let's talk about the first optimization, which is to adapt the indexes, or specifically secondary indexes for YugabyteDB. So for that, let's look at one of the tables that we copied over from Postgres to Yugabyte for this workload. So you can see a table here called pending settlement, and all it stores are payments that have been successful and are now ready to be settled to the merchant. So it has some fairly standard columns that you can expect, an ID, which is the primary key, the amount of the payment, what currency it is, which merchant the payment belongs to, so on and so forth. Along with this, there's also an index on this, specifically on the currency, merchant ID, and amount columns. And this was picked way back when we were building the Postgres workloads itself. So let's look at a query one of the common queries that run as part of this workload against this table. So this query is finding either the smallest or largest unsettled transactions. There are 2 flavors of this query that run. What this is doing is that it's picking rows from pending settlement that match a specific currency and merchant ID, and then they are sorted by amount, either ascending or descending, limited by some value in the thousands. And what this does is lets us periodically pick the largest or smallest payments. So what are the problems with this schema in terms of running this on YugabyteDB compared to Postgres? So because this is optimized for Postgres, it was working really well on Postgres, but not really on YugabyteDB. So one of the first things we saw was that currency is not a good partition key. So by default, when you create an index in YugabyteDB, the first column of the index becomes the partition key. That's the column it uses to distribute the data across the different nodes. So for example, if you can see here, if you look at nodes, all the GBP payments are in one place, all the USD payments are in one place, all the AUD payments are in one place, so on and so forth. The reason this is not a good partition key is because not all currencies are created equally. Some currencies have much larger trading volumes and hence significantly more payments. And when you put all of those payments on a single node, that node becomes the hotspot and receives much larger query load than the others. So to solve this, what we did was we swapped the order of the 2 columns such that merchant ID became the partition key. And turned out this was a much better partition key because it distributed the load a lot more evenly across the different nodes. And as a result, the queries as themselves were more evenly distributed across, and we saw better throughput. Another issue that we saw with this query pattern was that the query fetches more rows from the table than there are in the index. And it needs to get these extra rows from the primary table. This happens in Postgres as well, but it's not a huge problem because in Postgres, all the data is on a single node because it's a single node database, which means that there aren't any extra network calls that you have to do which add latency. However, if you look at how things are on Yugabyte, the secondary index is distributed differently from the primary table. So the index, which is in blue here, is partitioned by the merchant ID, as we just saw. But the table, it's distributed by its primary key, which is ID. What this means is that for a given row, the row in the index may not necessarily be on the same node as the primary table itself, which means when you need to fetch the extra rows from the table as part of the query, you now have to do a RPC. Now this adds extra latency to the read query as it has to make a network call, which is not something that you had to do in Postgres. To solve this, we used covering indexes. So you can add an include clause to an index followed by a couple of column names. And what that does is that alongside the index, it also stores some extra columns as part of the index. This makes the index larger, but what this means is that if you do a query and the rows you need are part of the covering index, it never has to reach out to the primary table, and you don't have to incur that cost of that extra RPC network call. All of this reduces the latency of the query itself. And the final thing we did to improve queries and the indexes was to look at how the different flavors of ascending and descending queries work. So one of the things we noticed is that compared to Postgres, where we saw similar performance for both flavors of the queries, both when you order by amount ascending and amount descending, we saw same performance, but this was not what we saw in Postgres, YugabyteDB, where the descending queries were significantly slower. Now, if you look at the index on top, the amount is sorted ascending in the index. One of the things to note here is that Postgres and YugabyteDB use different data structures for their indexes. In Postgres, it uses something called a B tree. And the way B tree data structure is laid out, you have similar performance if you had to scan an index forward or backwards. But this is not the case in YugabyteDB. YugabyteDB uses an LSM tree or log structured merge tree, in which the forward scans are a lot more efficient than the backward scans. And that's because the way the data is stored is different. So the way we solved this was to add an extra index for the descending case. Most of the index looks the same. The main difference is that in the descending, you have a separate index where the amount is sorted by descending to serve the descending query. And that's where we saw similar performance on both the ascending and descending case. However, one thing to note here is that extra indexes mean that you have to write more on your write workloads. So this is something to keep in mind, that you have to make a trade-off between optimizing for your read workloads and the write workloads. So just to summarize, the way we adapted our indexes was to pick a good partition key, introduce covering indexes to convert index scans into index-only scans, and then adding separate indexes for specific use cases such as backward scans in this place. So going to the second optimization, which is to parallelize bulk updates. As we've talked about before, we have optimized heavily for Postgres in the past, one of which is large bulk updates, because that works really well on Postgres. But what this means is that the jobs for the larger merchants are slower because there are many payments. Now, we see this on Postgres as well, but this is more of an issue in YugabyteDB because the distributed nature of the queries amplifies that difference in latencies. So one of the ways we solved this was to realize that actually we have more than one node in the cluster to execute queries against. So why don't we just maintain database connections against all of them, split the queries such that instead of having one large query that updates 3,000 rows, you now have 3 queries that update 1,000 rows each, and then just execute them in parallel. Effectively, what we're doing here is you're horizontally scaling the query. Now, this was really good for us because this was horizontally scalable. As we did this optimization, we realized that the largest merchants were now running faster on YugabyteDB compared to Postgres. And one final optimization that we did was to minimize storage flush requests. So if we go back to the schema, you'll notice that the function that we use to generate the ID primary keys is a custom function, which is the reason we do this is so that we have standardized ID formats. But however, when we were doing large bulk inserts, so in this case, 5,000 rows, we saw that writes were being flushed one row at a time when using this procedural function. And this is because the procedure is stateful, which means that Yugabyte can't buffer the writes and needs to persist each row before calling the function again. We took a fairly straightforward solution here, which is just to use simpler IDs. We moved to UUID4 instead of using our custom format, and this allowed us to leverage inbuilt functions rather than our own custom procedural functions. As a result, we could leverage the buffered writes. As you can see here, even though there are 5,000 rows to write, it only did the flush request twice. And overall, these kind of queries sped up by 30 times. So just to summarize, these are the three optimizations we did: was to adapt the indexes for Yugabyte, parallelize large bulk updates, and to minimize storage flush requests. So how did we do after all of these optimizations? So the good news is that at the end of this, overall throughput was now higher on YugabyteDB compared to the Postgres workload counterpart, even with similar number of database cores. And what was even better was that these were now horizontally scalable, such that the largest merchants were now more than 2 times faster on YugabyteDB compared to Postgres, which would buy us a lot of runway for the future. So with this first workload migrated, what's next for us? So what's next for us is to migrate the rest of the database. We need to do this if we want to truly realize the benefits of distributed SQL and scale our processing. This would be a larger challenge in the first workload because given the size of the database, we have hundreds of tables spanning terabytes of data. One of the learnings that we had from the first phase was that while manually migrating workloads within the application is a great way to learn distributed SQL because you get to learn, you interact at a low level with the database, it doesn't really scale to a larger application. So one of the things that we will be doing is exploring a tool that Yugabyte offers called YugabyteDB Voyager, which is a tool that orchestrates the full migration lifecycle, starting from schema migration, data migration, tuning performance, live cutover, and even doing a fallback if necessary. So hopefully this will simplify many of the things we had to do manually, and we can then focus on some of the bigger problems as part of the next phase, such as optimizing all those tables and queries at scale. Thank you. That's all from me.